Where we've been. Last day we worked this problem. We found that at point A, the block had 80 joules of gravitational potential energy. We got that from our formula mgh, where m was 10, g was 10, and h was 0.8. We found that this frictionless track did no work because it was always pushing perpendicular to the motion, and so we still had 80 joules when it got down to point B, but now that energy was kinetic energy. And then, as it scraped across that rough section, it was robbed by 60 joules. We found that the friction force was 30 newtons, and it acted for 2 meters, because the friction force was one way, while it was moving, the block was moving the other way. That was negative error. So I take the 80 joules, I subtract off the 60 joules that it was robbed, and it's left with 20 joules. And then at the end, we calculated the compression of the spring. Let me just remind you how we did that. It's an energy problem, so we always start here. Energy initial plus vert is equal to energy final. I want to know how much the spring is compressed when the block stops to turn around. So I want one of these points to be the turnaround point. Oops, spelled with a D. And the initial can be any other time. Because I know that there's no vert done between C and the turnaround, it would be simplest just to take my initial to be C and say there's no vert between C and the turnaround. That means at C I've got 20 joules, and that at the turnaround, all of the energy's in the spring energy, because the block has to stop to turn around. It's still on the level floor, and so that's just going to be 1/2 times the spring constant of 160 newtons per meter times the delta S squared. If I solve this for delta S, I get 1/4 is equal to delta S squared, and that gives me a delta S of 1/2 meter. So it compresses the spring by 1/2 meter. Now I just want to point out that I could have written this problem backwards. I could have written it this way. A block of mass 10 kilograms slides from rest down a frictionless ramp such that the center of the block drops a distance h. As the block passes from B to C, it encounters a 2-meter section of track that is rough, having a coefficient of kinetic friction of 0.3. After passing point C, the block compresses a spring by an amount 0.5 meters and comes to a momentary stop. Find H. Well, in that case, I would start where I always start. I would choose the turnaround point because I know everything about the energy there. I would choose this as point A because I want information. I want the height at A, and this would be the work that happens between A and the turnaround. So at A, I would say, well, I've got 10 kilograms. G is 10 newtons for each kilogram, and this is times H at A, minus the 30 Newton friction force times 2 meters is equal to 1/2 times the 160 Newton per meter times the 1/2 meter squared. And suddenly it's algebra. And we solve for H and we get 0.8. Okay, you can dance frontwards or backwards unless you're a guy. Okay? Questions on that? Okay, I found this on the internet. You got this 3-kilogram object to release from rest. It comes down this curved frictionless ramp, and there's a spring at the bottom. Part B says, does the object continue to move after it comes to rest? If yes, how high will it go up the slope before it comes to rest? And this student said, no, there is an elephant in the way. It's a parable for our time. Okay. Now, this problem that you voted off the island came from an old exam. It was the first problem on the exam. It was intended to be a gimme. It was intended that everyone would get it right and feel warm and fuzzy. That's not the way it turned out. Okay, that's not the way it turned out. Now, we have Tarzan starting from rest, 5 meters above the water. He swings down, releases, and flies through the air. My question to you is, true or false, energy is conserved in this problem? True or false? Okay? True is the correct answer. We came really close to having 100% there. If we think about what would do work, well, the Tarzan swing, but it's always pulling along the vine, and Tarzan's always moving perpendicular to the vine. So by our definition of Varric, that's zero Varric. If we ignore air resistance, and we always do, then there's no loss of energy due to air resistance. And so we can use conservation of energy. Now initially, all of the energy is gravitational. Tarzan's not moving, and there's no springs in this problem, and so that is the total energy. If energy is conserved, then right there when he lets go, I still have the same amount of energy. But now it's divided between 2 buckets. If I look right before he hits the water, right before he hits the water, right before he hits the water, don't let him hit the water. If he hits the water's doing a whole bunch of negative Varric on him. That's hard to calculate. That's really messy. You want right before he hits the water, how fast is he going? If energy is conserved, and it is, and all of that energy is now in the kinetic bucket because he's down at height 0, then I can figure that speed out. Now here's the problem. When we put this on an exam, we gave them those 2 meters. And everyone in the class felt they ought to use them. Well, the point we were trying to get at is that if you want information here, and you know everything about the energy there, make that your initial and that's your final. And you do not have to care about anything that happens in between. If he's really good, he can do a triple flip with a full twist. It doesn't matter. It affects how much fun he's having, but it doesn't matter to the final answer. Now, here's what many, many people did. They used energy to figure out how fast he was going here. Pretty straightforward. But then they used a whole lot of trig to figure out what angle he was going at. Then they turned it into a projectile motion problem with very ugly numbers, and they got lost. It took them a whole heck of a lot of time when they should have been working on the rest of the test. What they needed to do was just say, the gravitational potential energy there is equal to the kinetic energy there. And because they both have a mass in them, the mass cancels. And if I solve for V, I just get a very simple answer, 10 meters per second. See if your neighbor followed that.
I did.
Okay. Quick follow-up question. Which person, the person on the left or the person on the right, strikes the water with the greater speed? The same. Now, a different question is, which one is having more fun? I mean, this guy knows what he's doing. That's the very first time that guy's ever done this. But they land with the same speed in either case. In either case. Now, folks, let's look at that problem that you just turned in, problem 11. And I want to just apologize for it. Originally, this was Steve Iger that was hit in the chest with the arrow. And this was the problem that launched the whole feud. And here's the thing. I didn't write this. This was written by two guys that were drunk at 2 o'clock in the morning in a bar. I mean, we were at a conference, and I went to bed early. I'm the Mormon guy. And my two friends, Jeff Adams and Tim Slater, stayed up, got a little tipsy, and they wrote this problem. Jeff and I were team teaching the class. We were going to give an exam, and they were proud of that problem. The next morning, I tried to talk them out of it. I said, this is mean. This is really, really mean. Oh, no, it'll be fun. It'll be fun. So anyway, the next test in Iger's class, every single cell of my body was turned to ooze. And then it was game on. I mean, then we just went back and forth. And this escalated and got worse and worse until I was visiting the Headwaters Academy over here. I was evaluating one of the science teachers. And this wonderful, brilliant young lady came up to me after class and said, so, how's my father going to die in your next exam? And then I thought, no, we've gone too far. We've gone too far. Okay, so in this problem, we have the crossbow, and essentially it's just a compressed spring that's going to push an arrow. That arrow has a mass of 0.05 kilograms, and the spring has a spring constant of 80 newtons per meter, and we compress the spring by 1/4 of a meter. This is being launched out of a window that's 10 meters above the street, and we're asked in part A for the initial energy. Well, we ask ourselves always the same three questions. Is anything with mass moving? No. Is anything up off the floor? Yes. Are any springs stretched or compressed? Yes. So when I plug in 0.05 kilograms, 10 newtons for each kilogram, times 10 meters, plus 1/2 times, that's an 80, times 0.25 squared. This is going to give me 5 joules, and this is going to give me 2.5 joules, to get a total of 7.5 joules. Now, the arrow is launched, and when the arrow gets to Steve Iger's chest, we want to know how fast it's going. Now, here's what started the fight. Steve had no problem whatsoever being killed in our exam. That was fine. But when we said, let's assume that the height of Steve Iger is 0. I mean, he said, hey, you calling me short? Maybe. And so that's when it happened. So we essentially just say energy initial is equal to energy final because we ignore air resistance. We've got 7.5 joules and it's all kinetic if we call his height 0. And if we solve for V, we get 17.3 meters per second. Now, the last part is just truly, truly disgusting. we assume that that arrow embeds itself 0.1 meters, and we're asked what average friction force does his body put on the arrow. I mean, if you're not disgusted by that, you can watch Game of Thrones. Anyway, here we just use energy initial is equal to energy final, except when it's not. We've got 7.5 joules of energy. When it stops in his chest, we have 0. And that's not the same because there's a friction force doing negative Verc over a distance of 0.1 meters. And that gives me the friction force of 75 newtons. Check that your neighbor got that right. And that your neighbor, please check that your neighbor's disgusted. Because they should be. Okay, we need one last idea before we move away from energy. And it's an idea that you've already encountered in your tutorial last week, and that's the idea of system. If I were to get this system started, what you see is that it eventually just slows down and stops. Now imagine if I could get rid of all the friction between the track and the cars and ignore or get rid of any air resistance. In that case, these guys would just keep on going back and forth, back and forth, back and forth forever. And yet the springs are pushing and pulling, sometimes doing positive Verc and sometimes doing negative Verc. And so how is that not changing the energy? Well, it's all about system. In general, we've been talking about 3 different buckets: a kinetic, a gravitational, and a spring potential. And we add those together to get the total mechanical energy. However, some problems don't demand all 3 buckets. For example, if I were to define my entire system to just be the block, if I draw my red circle around the block, and that's my system, can I talk about the kinetic energy of the block? I can, because the block's part of my system. Can I talk about the gravitational energy? I cannot. Because gravitational energy is an energy that is between this bucket and the earth, pulling on each other. There's not gravitational energy just in the bucket itself. It's in the bucket-earth system trying to get closer to each other. If the earth wasn't there, I could put this above your head and it would just float there. Okay? So without the earth in my system, I can't talk about this bucket. Likewise, if the spring's not in my system, I certainly can't worry about spring potential energy. That's not part of my system's energy. Now, if I look at just that system, I've got one bucket. And watch what happens to that bucket. When I release the block, when I take the hand away, there's no energy in my kinetic energy bucket. Then it gets started, I get some kinetic energy. Then it's going really fast when it gets to equilibrium. And then it goes past the equilibrium and it starts slowing down. The spring is now pulling back. And then it gets to a turnaround point. And this is what happens that total energy bucket is filling up, emptying out, filling up, emptying out, filling up, emptying out. And that's because the spring is sometimes doing positive Verc to put energy in, sometimes doing negative Verc to take energy out. And that's a very messy system. For one thing, calculating the Verc done by a spring requires calculus. That's ugly. I don't want to do that. So the alternative is to redefine my system such that it includes the spring. Now if I do that, I can talk about kinetic energy because I've got the block. I can talk about spring energy because I've got the spring. I still can't talk about gravitational energy if I don't put the earth in my system. Okay? Now, watch what happens as it goes back and forth. I release the block. Initially, all the energy is in the compressed spring. And then the spring relaxes a little bit, but now the block is moving. So now some of the energy is in the kinetic bucket. When it gets to equilibrium, the spring is neither stretched nor compressed. All of the energy is in the motion. Then it goes back past equilibrium, the block slows down, and the spring now is stretched. And then it gets to a turnaround point where all the energy is back in the spring. Now watch what happens to the total energy bucket as this block goes back and forth. That's a system I can work with. The energy sloshes back and forth between the two buckets, but the total energy stays constant as long as we have zero friction on that floor, and we usually do. So that's the way I want to define my system. Now, what that suggests is that when I presented you this Varick energy equation and told you that it was the one equation to rule them all and in the darkness bind them, I was lying a little bit. This is what I taught you. That's the truth. Okay? It's only external Varick that can change the energy of a system. If I sit on this table has wheels. If I sit on this table and push on my back, I don't go anywhere. That's one part of the me pushing on another part of the me. It doesn't get me anywhere. I got to push on something outside of the system in order to change my energy. Okay? So, how do we define our system? What do we put inside the big red circle? This is my suggestion. Always include anything in the problem with mass that's moving so that you can consider the kinetic energy in the problem. Secondly, we will always, always, always include the earth in our system. And by that I mean the gravitational force. You should never, I repeat, you should never calculate the Varick done by the gravitational force. You should instead talk about the energy stored in that potential energy bucket. Consider this. If I raise this up, what's your name? If I raise this up above Jake's head, we say it has more energy. It has a greater capacity to do damage to Jake. But that only makes sense if we only count my Varick, right? As I lift this, I'm pushing up while it goes up. I'm doing positive Varick. But at the same time I'm pushing up, the earth is pulling down. The earth is going to be doing just as much negative Varick as I'm doing positive Varick. But I don't include them both. I don't let them cancel each other out. Because the earth is an internal force. That's one part of my system pulling on another part of my system. I'm the external agent that's changing the energy of that system, increasing the energy. Okay? Now, the last thing would be any springs in the problem. Include those in your system so that you can talk about spring potential energy. Again, that means you will never, ever calculate the Varick done by a spring, which is a good thing because that's something that requires calculus. So what are the external agents that do external Varick? No, not them. Is that James Bond to you, or is it one of these guys? Yeah, no, not that guy. No, that guy. Now, you should always leave frictionless ramps and Tarzan swings out of your system. Why? They do no Verk. It's not going to be any trouble to leave them out. Okay? If you leave the floor out of your system, you can calculate the Verk, usually negative Verk, done by the friction force by the floor. The lobster hand can do positive Verk if it's pushing in the same direction as the motion, or it can do negative Verk if it's pushing opposite the motion. We saw that with the rocket sled. And anything else that's not this, this, or this. If you use that system, then the problem will be simple. It will be 2 steps of physics and then algebra. Now, how many of you know who Richard Feynman was? Okay, one of the greatest physicists of our time. He got a Nobel Prize for teaching us, predicting that what we thought were elementary particles, protons and neutrons, that they were made up of something smaller, the quarks. And he gave us color chromodynamics, quantum chromodynamics, I should say. And he was really a very interesting individual. He was known for not being able to sleep, and so he would roam around when he was on the project to build the atomic bomb, and he would roam around the lab and find out what people were working on. People would come in the morning and find their problem solved. He did the same thing at Caltech when he was professor there. I was able to watch him teach once. When I was at MIT as a graduate student, I heard that the great Richard Feynman was coming to give a guest lecture on quantum mechanics. I wanted to get a good seat, so I went an hour early. I found that the great big huge lecture hall was packed. I had to stand in the back. It was an hour and a half. It was the most profound lecture I have ever experienced. I will never forget that experience. It turns out that Richard Feynman taught for many, many years at Caltech, and he always taught the courses for the graduate students that had very few students. One year they came to him and they said, you know, Richard, we'd really like you to teach the freshmen, teach the introductory physics class. We think that they would benefit from that. So he agreed and showed up. And when he showed up the first day, the big lecture hall was packed, just like at MIT. The freshmen were there, but also the grad students were there, and the postdocs were there, and a lot of professors were there. And he started giving introductory physics lectures. Now, a couple months into the semester, the room wasn't so packed. The professors were still there, the grad students were still there, the postdocs were still there, but most of the freshmen had dropped out. He had pitched that just a little bit too high. Now, one of his friends recorded all of his lectures, and then later put them into a 3-volume set called the Feynman Lectures on Physics. Now, this is where physicists go to learn physics. When they're confused about a concept, they go to the master and they watch how he teaches it. And these books are, to me, priceless. Well, I want to share with you something out of Volume 1, Chapter 4. And this was right at the beginning when the freshmen were still in the class. And he was trying to teach those freshmen about energy. And he told them a story about a young boy, a little bit spoiled. His name was Dennis the Menace. And his mother was a little bit controlling. Now, Dennis had 28 identical blocks. And every day his mother would come in and count those blocks to make sure they were always there. And every day she'd be happy when she saw all 28. Now, one day she came in, there was only 26. She looked all over, only 26. Then she noticed the open window. She looked out the window, and there on the grass were 2 blocks. She went out, she got the blocks, she closed the window, and she boarded it up. She nailed it shut. She's controlling. The next day, she counted the blocks and she found that there were 3 extra blocks. How could this be? Then she realized that Bruce had come over to play, Dennis's friend, and he had brought 3 of his blocks. So she sent Bruce home with his blocks, and she said he's forbidden from ever coming back to play. She's controlling. Now that went fine. She always counted 28 blocks every day, until one day she only got 25. Now she searched everywhere, she couldn't find the extra blocks, and then she saw a toy box that was closed. She went to open the toy box, she knew those blocks were in there, and Dennis said, "No, you may not open the toy box." He's a brat. But Mother's clever, and she waits for a day when she sees all 28 blocks. She takes the toy box, the empty toy box, she weighs it. It has a weight of 16 ounces. She takes one block, she weighs it, it has a weight of 3 ounces. And then, whenever she comes in to count the blocks, if she doesn't see 28, she weighs the toy box, keeps it closed, she can't open it. She subtracts off the weight of the empty toy box. The difference has to be blocks. She divides by the number of ounces in a block, and she gets 28 every single time. Until she doesn't. And then she notices that the bathtub has dirty water. So dirty you can't even see blocks that are submerged. So she waits until she can count all the blocks. She takes one block and she drops it into the dirty water. She sees that the level of the water raises from 6 inches to 6.25 inches. And then she revises her equation. This is the number of blocks she can see on the floor. This is the number of blocks that are hidden in the toy box. And these are the number of blocks that are hidden in the dirty water. Now, the great Richard Feynman turned to his freshman and he said, "What does this have to do with energy conservation?" And he said the first most important thing is that there are no energy blocks that you can see. You can't look at an energy block, oh, it's green. All the energy is hidden. It's either hidden in the toy box or hidden in the bathtub. Or in our case, it's hidden in the kinetic energy or it's hidden in the gravitational energy. It's just this profound principle that if you add up all these formulas, you always get the same number. As long as Bruce doesn't come over to play and we board the windows shut. Now what does that have to do with energy? Well, the windows and Bruce are how energy comes into the system or goes out of the system. The only way you can change energy, well, there's 2 ways. You can do work on the system. That's what we've got in our equation. The second way is you can light a candle underneath it. You can use an open flame. You can add heat energy. Now, they tell you all about that over in the chemistry department, and I'm happy to let them teach you that. In this class, we're only going to worry about work. We're going to ignore any heating as something that chemistry will handle. Okay? But the important thing is, if you can find these formulas that tell you where the energy is hidden, then nature will allow you to use that to solve problems. Okay? Here's a problem that's on your tutorial homework. It's half of your tutorial homework. And I'm going to help you work it right now. I'm going to help you get halfway done with your homework that's due tomorrow. Okay? We've got time to do this. Now, in this problem, we have a pendulum, which is just a mass on a string, and the string is quite long, 7 meters long, and we've attached it to the side of a barn, and so that pendulum, if it were just left alone, that's 7 meters. that pendulum would just swing down and up and back and forth and back and forth. If we ignore air resistance and we ignore the friction that happens right here at the nail, it would just keep on going back and forth, back and forth. But instead, we drive a nail into the side of the barn. And we do that a distance 6 meters below the pivot point. Now what happens is the ball at the end of the string swings down, and when it gets right here, it catches the nail. And suddenly the ball is forced to go in a circle. That circle has a radius of how big?
1 meter.
Yeah, that's 7 meters, that's 7 meters, that's 6 meters, so this would be 1 meter. A radius of 1 meter. Now, what we're looking for is how fast that ball is going at t equals t top. Right here, when it gets to the top of the circle. Now, the first question we have to ask ourselves is, what's our system? Well, we include the ball because it's moving and it has mass. We always include the Earth so that we can talk about gravitational potential energy. And that's it. Now, if we look at a free body diagram at some random location, we have the weight force down, Earth on the ball. We have the tension force by the string on the ball. And what we're looking for is any external varic. Okay, any external varic on our system. Well, the first thing we have to decide is, are any of these forces external forces? Well, the weight force is the Earth pulling on the ball. That's one part of my system, the Earth, pulling on another part of my system, the ball. That's internal. The tension force is exerted by the string, and the string is not part of my system. That's external. But it does no varic. It does no varic because it's always pulling perpendicular to the motion. Now, is the mechanical energy of the Earth ball system conserved from this time to this time? T equals 0 to T equals T top. Is the mechanical energy conserved, yes or no?
Yes.
Yes. You should be saying heck yes. Now, use that to find the speed of the ball at that point, T top. Really quick with your neighbor. You're working your homework. It's not wasted time. Okay? You get to turn this in. And when you get an answer, tell me what you get. And then we'll work it together. Last call. The answer is B. The answer is B. Let's work it together. I'm going to call this my initial state. I'm going to call this my final state. And I'm going to call my zero of height the lowest point that the ball ever gets. And that lowest point is going to be 7 meters below this pivot. Does that make sense? Now, if energy is conserved, at this initial event, the ball is not moving, and there's no springs in the problem, so all of the energy is gravitational. At this final event, the ball is moving, and it's also up off the floor, So I would have gravitational plus kinetic. Well, each of these terms has an m in it, so I can cancel the m. This is going to be 10 times 10 newtons for each kilogram times a height of 7 meters. This is going to be 10 newtons for each kilogram times a height of 2 meters. Do you see where I got that to? That's what I'm calling 0. From the bottom to the nail, that's 1 meter. It has the circle has a radius of 1 meter. But it's up here. There's a meter, so it's at 2 meters. And then I have plus 1/2 v squared. I solve for v, and I get v equals 10 meters per second. Now the rest of the problem, we have 2.5 minutes left. We're asked to find the magnitude and direction of the acceleration. Well, the acceleration is centripetal acceleration. That's v squared over r, or 10 meters per second squared over 1 meter, or 100 meters per second squared down towards the nail, towards the center of the circle. That's a big acceleration. If that was you, you'd be passed out. Now the net force is just the mass times the acceleration. We're told that the mass of this ball is 0.2 kilograms. The acceleration is 100 meters per second squared down, and that gives me a net force of 20 newtons down. Now if I draw a free body diagram of the ball at that top of the circle, there's going to be a weight force down, and if the mass is 0.2, this is going to be 2 newtons. There's going to be a tension force by the string on the ball, and that's the last part of the problem. How big is that tension force? If this diagram has to screen down by a net force of 20, how big does the tension force have to be? Okay, we'll do the pet of death on Wednesday, people. Bring popcorn, bring a friend.